Welcome back, everyone. In this video, we will be continuing the section on areas and distances. Now, I just realized at the end of the last video, there's one quick thing that I wanted to mention, and I'm going to mention it now. You may have read on in the notes and said, note that f of x star, this is supposed to be an I as well. F of x subscript I star just means that the x value to plug in depends on the interval and whether you are using left, right, or midpoint x values, sort of how we described it. So a lot of people put a star here to say it could be a lot of different things. There's not just a basic formula to figure out what x value you're plugging in. If you don't like that star, then you can just completely leave it off and leave it as xi. I prefer just leaving it as xi, but I know a lot of books, maybe if you look at Wikipedia for this stuff, you're probably going to see a star, and that just means this can really be anything inside the interval. But we're using the specific situation where all of our intervals have the same length or base, and therefore it's probably easier just to leave this off. All right, so what I want to do here is kind of really just go through the example that we outlined in the previous. We'll use 4 rectangles, but what we want to do is approximate the area between the x-axis and y equals x squared on the interval 0 to 1 by using 4 rectangles with a base of equal length. So this is really important because if we didn't have a base of equal length, then what would happen is we would need to make sure we go through and adjust. So just to sort of describe what would happen here, we're not going to worry about doing problems that aren't of equal length. But let's say you only had 2 rectangles here, but one was, twice as long as the other. One was from 0 to 2/3 and one was from 2/3 to 1. Well, then the base of that rectangle would be 2/3 and the height would be whatever x value you're plugging in. And so really a formula like this doesn't work because you have to actually have different bases. This formula assumes all the bases are the same. All right, but we're first going to do it with right endpoints, then do the same thing using left endpoints. And really what I want to show you here is that when you're doing right, whether you're doing right or left, you're pretty much doing all the same work repeated. So when I do the left endpoints, I'm not going to have to do much more work. The most important thing, you don't really need to graph y equals x squared, but you should graph your interval with the number of rectangles split up and then point out the x values to plug in. That's really the main thing. And also pointing out b minus a over n. So a is 0, b is 1, and n is 4. Remember, a is the x starting value, b is the ending x value, and n is the number of rectangles, and we are told to use 4. So go ahead and let's figure out b minus a over n. It's part of our formula, and we'll just leave it on the side for now. So we got 1 minus 0 over 4 is 1/4. Now, whether we're doing right, left, midpoint, anything, we could be told what x values to plug in. This is our b minus a over n. Now, the other thing we want to go ahead and do, and I'm going to focus on right endpoints first because that's what we want to do first, is make a number line. So imagine that I'm kind of just going through this problem, but instead of drawing the entire graph with all the rectangles, I'm just going to draw the x-axis. That's all I'm doing here. So I'm visualizing the x-axis and what's going to happen here. We're starting at x equals 0. We're going to end at x equals 1. And I want to split it into 4 equal length intervals. So that means I'm going to make 3 hash marks here. Try your best just to make them look equal length so you know it is equal length. But this time we do need to specify the x values. So what's happening here, we actually know the width of every rectangle already. So that's why it could be useful to do b minus a over n first, is you just add the b minus a over n every time, and you'll get the width here. So basically what we're saying here is that the base from rectangle 1 starts at 0 and goes to, well, we're going to add 1/4 to that. 0 plus 1/4 is 1/4. Then rectangle 2, we're just going to add the same thing, and that's 2/4. 1/4 plus 1/4 is 2/4. And yes, you can simplify this to 1/2, so go ahead and do that. But I like to keep the denominator there because it just makes it easier when you keep adding. So when we add 1/4 to 2/4, we get 3/4. And then when we add 3/4, or add 1/4 to 3/4, we get to the 1. So every one of these, single one of these has a base length of 1/4, which is exactly what we want. And this is a lot more decorated than I would normally do. All I would normally do is just have this number line, and I would put the 1/4, 1/2, and 3/4. I wouldn't add this, but I want to emphasize that what we just did is all these are length 1/4, and we have 4 of them. All right, now for the right endpoints, the x values for the right endpoints. We're going to plug in 4 of them because we have n equals 4. And each one of these represents the base of one of our rectangles. So from 0 to 1/4, we would want to plug in the right one, which is 1/4. And then from 1/4 to 2/4, we would want to plug in 2/4, or better yet, 1/2. And then from 2/4 to 3/4, we would want to plug in the right one, which is 3/4. And then from 3/4 to 1, we would want to plug in the right one, which is 1. And it's, always helpful to think of right, direction-wise, but it's always the bigger one as well. It doesn't mean that your answer is going to be bigger for right endpoints compared to left. All it means is that you're plugging in the right one, the one further down with bigger x values. Now, one thing I want to go ahead and do, even though we're not going to solve it until later, is just point out the x values for the left endpoints, because what you're going to see is a lot of repetition here. Now we're going to go through and look at the same exact intervals. So the first rectangle starts from 0 to 1/4. The left is 0. Now the next one from 1/4 to 2/4, the left x value is 1/4. And just so I don't hide it, I'll plot it above. So it's 1/4. And then the third intervals is from 2/4 to 3/4. So the left value is 2/4 or 1/2. And then the final interval is from 3/4 to 1, and the left value is 3/4. So what's going to happen here is, yes, we need to plug in these x values and add them together. That's what this is saying. But when we do the right endpoints, we're actually going to cover 3 of them already, the 1/4, 1/2, and 3/4 for the left one as well. So we're actually going to do most of the work for the left one when we solve the right one. All right, so what do we want to do? We want to go ahead and plug in all of our x values and then add them together. So for the right endpoints, we have f of 1/4. We have f of 1/2. I'm actually going to leave this as 2/4 just because when we plug in everything and add it together, it'll probably be easier if we have the same denominator. I'm going to plug in f of 3/4, and I'm going to plug in f of 1. And if you want to write 1 as 4/4, you can. Nothing wrong with that. But this is pretty much the only point now where knowing your function, f of x equals x squared, pops up. We do technically need to know that this graph is not below the x-axis, but hopefully you know that x squared is that parabola, so it only touches, it never goes below the x-axis. All right, so we plug it into f of x here. We get 1/4 squared, which is 1/16. Then 2/4, we plug in 2/4, and then we get 2/4 squared is 4/16. And yes, that simplifies, but for the sake of having to add these together, it's probably easier to leave it like this. Then the next one, we have 3/4 squared. And when we do that, we get 9/16. And then lastly, when we plug in 1, and if you want to, you can write it as 4/4 squared, because we're going to have to do that when we add this together, but 1 squared is 1. Right? And what our formula says is now add all these together. Add all these together. Now it's probably just, easiest when you're doing this to go ahead and use a calculator. Just make sure at the end of the day you're getting a fraction. 1/16. We've done tons of problems finding a common denominator, so you should be comfortable doing that, but you should maybe practice some more if you need to. All right, so if we add all these together, we get 15 over 8. So I'm going to go ahead and write this as 15 over 8. And once again, if you do that by hand, you should see that 15 over 8 happen. All right, now think about exactly how I described this formula. We figured out all the x values plug in. We plugged them in and added together. This was our 15 over 8. Now we multiply by b minus a over n, which is 1/4. So now the area for the right approximation is equal to 15 over 8. That's our functions added together, and we multiply it by b minus a over n, which is 1/4. And 1 times 15 is 15 over 4 times 8 is 32. And if the fraction doesn't simplify, then that's good to go. And now we just go through and do the same thing for left. So this would be our right endpoint approximation. Now for our left endpoint approximation, we want to plug in the x values of 0, 1/4, 1/2, or 3 or 2/4, whichever one you want to think about, and 3/4. But the nice thing is that, like I said, these last three we've already done. So we know f of 1/4 is 1/16. We know f of 2/4 is 4/16. We know f of 3/4 is 9/16. And this becomes a lot more helpful when your function's a little messier. It's not just x squared. And then f of 0, well, our function is x squared. So this is 0 squared, which is 0. But for the left endpoints, we're doing the same thing. We're adding them together. And then what happens when you add these together? These already have the common denominator of 16, so we just add them. 1 plus 4 plus 9 is 14 over 16. And we can simplify that because they're both even to 7 over 8. Right. And then we want to finish by doing the left approximation. Now that we've added all the function values together like this, we have 7 over 8. And we multiply by b minus a over n, which is the same thing again, 1/4. And you get 1 times 7 is 7 over 4 times 8, which is 32. And now left approximation is not necessarily smaller than right approximation. It just depends on what your curve looks like. If it is increasing, it will be smaller just because really the picture. So if I draw graph y equals x squared real quickly, and I zoom in on just 0 to 1, because that's all we care about. You can imagine from here, if we're choosing bigger x values, which the right endpoints do, then the height of the rectangles is bigger. And that's really why I wanted to use the same curve as our original example, is because that really shows that the left endpoints had much smaller rectangles. Oops, let me go ahead and get rid of that. Than the right endpoints with our example. Right, but don't try to look too into whether right or left is always bigger. That's not really important. Oftentimes, especially when we talk about distances in their examples, it's not so much knowing the right or left, it's about knowing the upper or lower approximation. And what you do is you just evaluate both. You do the left and right approximation, and whichever one's bigger is your upper approximation, and whichever one's smaller is your lower approximation. Right, but once again, just really summarize this problem. The point is, when you do left or right, you're doing almost all of the same things together. Now, I did mention before, we did talk about the midpoint. You can do any pattern of x values for any interval. As far as midpoint goes, that's just another option, but we really don't deal with them much. So don't worry about them because that's not really what we're going to be focusing on. All right, now distances. So specifically, if y equals f of x specifically represents a velocity function, then the area under the curve represents the distance traveled. And to see this, I want to look at a basic example to really explain this. So it says, let v of t equals 50 be the velocity you are driving at time t in miles per hour. So you're just driving constantly 50 miles per hour. What is the distance traveled over 4 hours? Now, if you can kind of interpret this and maybe you come up with 200, and that should be correct because this is saying you're going 50 miles per hour. If you do that for 4 hours, it's just 50 times 4. But what we want to go ahead and do is relate this to the area under the curve. So this is going to be a graph. I'm just gonna, it says over 4 hours. It doesn't really tell us what t value. So I'm gonna pretend we're starting at t equals 0 and going to t equals 4, which is 4 out. And this is gonna be time in hours. But kind of the point here is that this graph is going to be at a horizontal line at just y equals 50 because it is just a number. So this is v of t equals 50. Now in general, when we're talking about time, we don't think about negative time, but just to really sort of just graph the whole thing, this is what the graph of v equals. Now we want to find what? I really am talking about relating this back to area. So I want to find the area of this, starting at t equals 0 going to t equals 4. Well, and you know, this is a shape that we know the area of because this is a rectangle. Since this is a rectangle, what we can do is we can actually just go ahead and compute without approximating with rectangles. So the area, which equals length times width or base times height, whichever one you want to do. The base is 4. And you can really think about this if you're in referencing what we've been doing. It's the number of rectangles when n equals 1. So b is 4, a is 0, n is 1. 4 minus 0 over 1 is the 4. And then its height is 50. And what is 4 times 50? It's 200. And if we want to tack on our units here, because we are talking about units, we have miles. And if you want to see the units happen, the 4 is miles, or sorry, the 4 is hours because we're traveling for 4 hours. And the 50 is miles per hour. So when we multiply these, not only do we get the 200 for the just representing the area, but the hours cancel out and our units actually come out to be exactly what we want, which is miles. But the point here is that, you know, this was a super straightforward example because we didn't really have to approximate it, but we can see that the area under the curve is related to going backwards. We start with a velocity and we get the position or distance traveled. And that's going to be a very big thing going forward. This is really our first example kind of understanding that when we find the area under the curve, it's like approximating something with the antiderivative because we're going backwards. And it'll take a couple more sections until we can really formalize it. But at this point, just really wanted to expose you to that. And we'll see an example in the next video, really talking about what happens or when do we actually use the idea of approximating with rectangles. It's usually not when you have a curve with a formula, but when you have data points. So we'll see that in the next video.